And if we apply now dynamical decoupling to the NV centers, we are able to improve the coherence time. How much do we improve this coherence time? Well, it depends on how quick we can apply the dynamical decoupling, the spiral pulses, on the NV centers. It tends to be quite faster than this coupling between the NV and the nuclear spin in order for it to be effective. If we were able to apply the pulses infinitely fast, so going down to a pulse spacing separation to 0, we would completely refocus this type of noise. Of course, this is practically not possible, but we are still able to reduce quite a bit the coherence time, or if you wanted the decay rate of the nuclear spin, T2n, which is here renormalized with respect to the relaxation time of the NV center, the electronic spin, because this is what sets the total magnitude of our system. So if I didn't do anything, I would expect to be around here, 0.5. What is actually sort of counterintuitive is that for samples spacing separation, I can actually make my noise worse than it is if I didn't do anything. So this point here, which is above 0.5, and this is the theoretical line, show that if I apply my pulses at some wrong times, I could make things even worse. This is for our engineered noise. Okay? If we consider the whole system, it's the fluctuator is a 3-level system, while in the engineered noise we were only using 2 levels. And so things are slightly more complicated. We can still achieve perfect decoupling, but then we need to pulse between the +1 and -1 level of the NV centers. And this is a true photon transition, so you don't have that directly if you just use microwave driving. You have to do some composite pulses, or now we are also exploring some more crazy ideas of doing mechanical driving to drive that transition, which sounds quite interesting. So indeed, to reach here, you need this +1 to -1 driving. Otherwise, you would only reach this optimal point here. So here, what we can do, as I said, is limited at some point by how fast we can drive our system. And so what we wanted to ask was, can we then still take the knowledge that we have on our system and improve things even more by now applying real quantum error correction codes to this type of problem? And so here what we found was to look for some hardware efficient ways of correcting for one particular type of noise, this common fluctuator dephasing noise, which indeed appear in our system, but could be considered also more general, for example, some random fluctuator close to superconducting qubits, or other system in which you have, again, spins coupled to some nearby fluctuator. So it's a model, noise model that, of course, to me is very relevant because it appears in my system, but I think that it's more general. And especially the lesson that we learn by looking at this, I think it's indeed quite interesting. So what is the type of system that we have in mind? So again, we are thinking about mostly our NV centers, but it can be generalized to something broader than this. So in the NV center system, we have this electronic spin, and then we have, instead of considering just the nitrogen, we might also have some carbon-13 around the NV centers, which are also spin 1/2, and so they could be used as memory qubits, for example, in a quantum repeater scheme or for some other task. Again, because they still have some quite strong coupling to the NV center, on the order again between megahertz and kilohertz if they're close enough, the main source of noise is not the coupling to other nuclear spin, is not phonons, for example, but it's really the presence of the electronic spin nearby. And again, the idea is that you will have some energy which describes the coupling between the carbon-13 and the NV centers. And now how much energy the nuclear spin feels depends on the state of the NV center. Again, it will be plus this coupling G if the NV is in the +1 state, minus G if it's in the minus state, or 0 if it's in the 0 state. And this fluctuator will indeed jump between all these 3 states at random, so we cannot really know when the jump has occurred, and so we cannot really correct for that directly. But indeed, we know a lot about our system. So if I have more than 1 qubit, I know that if one error has occurred on one qubit because my NV has performed a jump, also all the other spin will have felt an error. And so the time at which this error occur are always correlated, which is quite different from a very generic type of noise model where many of these correlations are not really considered. So if I consider what is the evolution of each individual nuclear spin, it will acquire a phase, theta j, which is just dependent on what levels my NV center, my fluctuator, have explored during the time of the evolution itself. Now I can also write everything in terms of a common theta by renormalizing my theta j by the coupling themselves. So all these angles, these errors are indeed random, but they are correlated with each other. And they have fixed ratio because they're just given by the coupling itself. I can expand my noise operator. So again, this is random, and so in general will give rise to dephasing. For small theta, I can expand in powers. And so to fourth order, at most what I will have is a sigma z error for on one qubit at a time. If instead I look at higher order, second order, third order, what I have is that I can also have a sort of a product between two different qubits, and so this corresponds to having error on 2 qubits, 3 qubits, and for the qt order, up to q qubits could have felt a correlated type of noise. So this is still a dephasing type of noise, so we could think about using the repetition code to correct for this. It's now a sort of rotator repetition code in the x basis, for example. So the 0 logical is the x state, and the 1 logical is the minus, 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 where these are eigenstate, the plus and minus of sigma x. And if I use something like this repetition code for larger and larger, I can also correct for higher order of my noise, but of course I will need more qubits. In particular, if I want to correct up to order q, I will need 2q plus 1 physical qubit, because the maximum error weight is indeed q. Instead, I can try to figure out if there is a code, a quantum error correction code, which is indeed optimized for this common fluctuator dephasing. And so we know that we only have an error on one qubit when there is also an error on all the other qubits. And so I can really exploit this knowledge. So I have this type of error, and not each individual error on each qubit. Everything occurs all together. And so what I can do is to indeed try to impose, to correct just for the collective error, the square of the collective error, etc., etc. And so we can find some codes, and my student David Layden is credited with finding this particular code, in where you can then optimize this coefficient R in order to achieve indeed the code which will correct for the noise. And you can forward tune with phases alpha and beta in order to find something which is actually sort of convenient to implement on your particular system. With this type of code now, you only need a logarithmic number of physical qubit to correct for a given order in your noise. And this is, of course, we are still considering small devices. So it's not that we are claiming that indeed you will have an exponential advantage in terms of a large system, because this will be a type of noise which intrinsically will only apply to some sort of localized type of system. But still, even if you just look at a small number of qubits, you can see that there is indeed an advantage. So here what I'm plotting is as a function of the noise strength, so how probable one of these noise occur, the effective average error probability that will occur on your qubits. And so the black line is just when I don't do any error correction at all. And then I can force check for our repetition codes, for example, for 3 and 5 qubits, how much error I have if I do the encoding. And indeed you gain a little bit, but only for very small error rates. Now if I instead apply the particular error correction code that we have optimized for this type of noise, what we see is that I have quite a huge advantage. And indeed, it's because for the same number of qubits, I can correct much higher order of my noise propagator. And so indeed, I can allow for a larger noise strength and still have quite a bit of correction. In order to find this code, we indeed need to know the couplings of the qubit to the noise, to the quantum fluctuator. And in practical terms, there will be always some like finite amount of precision with which I can know these couplings. And so we also check if indeed it was robust against some uncertainty in the coupling strength themselves. And so indeed, if you just have 1% uncertainty on the coupling, things do not change much. Okay, from here to here, you can see everything is sort of moved up a little bit. Okay. If we indeed increase quite a bit the uncertainty on the coupling, what you start seeing is that all the lines sort of collapse and they, in the end, will tend to the repetition codes. But this is indeed what we expect. If we don't have knowledge of our noise model, then it doesn't make sense to try to find something which is tailored for it. So it's not really surprising, it's not really limitation. It just, again, reinforces the idea that if you do know your system, then you can do better. If you don't, well, you're stuck with just quite general error correction codes. Okay, we sort of try then to apply this type of ideas not to general quantum computation, but to a particular task, the task of quantum sensing. How much time?
7 minutes until the end of the talk.
Okay. So I think that this part is actually the longest one, but it's the easiest one, and so I will present it quite rapidly, I think. Again, it's just another example of how we can use knowledge of our system, but also how we can exploit the fact that we want to do just one particular task and not general quantum computation in order to achieve some good protection of our system. So what is quantum sensing? Well, quantum sensing, again, is for this particular talk, is just a parameter estimation. I have some external field which couples to my system through some parameter. Here, for example, the parameter is the field, and it's coupled to my spin through its geromagnetic ratio. In my mind, I always think about spins, I'm sorry. But this can be more general. It could be some electric field coupling to an atom, for example. What you do is to prepare your qubit in a superposition state, let it evolve for some time, it will acquire a phase which depends on the parameter, and then you map this phase into something that you can measure, for example, population difference, and you measure it out. The signal-to-noise ratio, of course, is proportional, because it appears in this phase, to the coupling strength between your field and your qubit, and to the time that you let your system evolve. Of course, both of them are sort of a trade-off. If your system is very strongly coupled, then this gamma is very large, but your coherence time, the time that you might be able to let the system evolve freely, is limited by the coherence time. And so what you can have is something very strongly coupled, very big gamma, but your coherence time becomes very small. So this becomes very quickly just a classical sensor, because coherence is lost very quickly. In the opposite regime, we have something which is very long-lived, very long coherence time, but most probably it is because the coupling to the external world is very small. And so what you have is a quantum memory, not so much a sensor. And so our question is, can we use error correction to do better, to find a better trade-off between these two limits? Can it help us? And the idea of quantum error correction for sensing is very similar to what is applied in computation. Instead of having just a long time period during which you will acquire a phase, n times the phase that you will acquire in the unit time period, you interrupt it and apply some recovery operation in between to check if noise has occurred and correct for particular errors which might have occurred. What others have found are some conditions under which error correction for quantum sensing can indeed be applied. And the idea is that you still need all the conditions for quantum error correction to work, of course, because you're doing error correction, but there is still this trade-off which is intrinsic to to quantum sensing. Whatever you are trying to sense is an unknown quantity. It's a coherent error, typically, so it's a coherent interaction, but it's still something that you do not know. And so it looks very similar to some type of error. And so if you apply just a generic quantum error correction code, most probably it will also cancel out whatever you want to measure, and that's not really good. And so there is still this trade-off between try to protect your system as much as possible, in this case through quantum error correction, but try still to save the coupling to the field that you want to measure. What people found was that indeed, in a very intuitive way, if your noise looks too similar to the signal, then it's not possible to find the code. Only if the noise is somehow perpendicular, it doesn't really exist in the same plane as your noise, then you can distinguish the two. And indeed, how many people interpreted this was that if you had dephasing noise, maybe you could measure something along the sigma x direction, but you could not measure something along the z direction. That looks like a very intuitive interpretation of what these rules give you. Other drawbacks of this particular proposal for error correction for quantum sensing was that it was required to have noiseless ancilla. And as we said, there are some good low noise ancilla, but typically they're not completely noiseless. So we wanted to find something a bit more practical than this. So what we then investigated was the fact that maybe there is something else which can distinguish your noise. So as I said, the picture which was taken from here was to say, okay, I have noise along Z, let's measure something along X. But there might be something else which might distinguish your noise from your signal. When we do dynamical decoupling, that something else is frequency. Okay, so your noise spectrum sits at a different frequency than the signal that you want to measure, and so you can distinguish it. You can use, if you want, algebraic differences, x and y direction, x and z direction, but you can also try to use spatial correlation in order to distinguish between noise and the signal. And so, again, we looked at specific examples of particular noise model in order to figure out if indeed it was possible to practically find some error correction codes to do quantum sensing. And so what we wanted to do was, again, to measure something which is just an energy shift, okay, which is typically what any sensor is most sensitive to, in the presence of some noise which is still a type of dephasing noise. But now this dephasing noise has some correlation between the noise which happens at different qubits encoded in this matrix of correlation here. Still, even if they are all along the same direction, you can find some error correction code provided that this vector describing your field is not all in the correlation matrix here. So we could find some example with 2 and 3 qubits where things are easy to calculate. For 2 qubit, actually, this boils down to just the coherence-free subspace. Or maybe you can measure differences in the field and have a uniform type of noise. For 3 qubit, you can have, if you want to measure uniform Z, one possible code is the repetition code, depending on the various correlation that you have. But you can also have some more general and different type of codes if indeed your correlation matrix has some particular shapes. So for example, for this type of shape of your correlation matrix, we could find that if I don't do anything, I lose my coherence quite quickly, and so my sensitivity is not as good. But if I apply my active error correction codes, I get much better sensitivity. So the lower the sensitivity, the better, because you can sense smaller qubits. We extended this to more general condition under which you can indeed achieve quantum error correction for quantum sensing when you don't have noiseless ancilla. And the condition is that you need to have that all your Lindblad are commuting, and they're also commuting with your Hamiltonian. Under this condition, you can indeed find error correction schemes which do work even if you have ancilla which are all affected by the noise itself. And in collaboration with Liang Zhang at Yale, we found some example from this dephasing noise that typical in NB centers schemes, but also for bosonics channels. More generally, you can think that, especially for quantum sensing, the goal is not really fault tolerance. As long as you apply some error correction code, which just improves your sensitivity, even if you're not noiseless, then you're still winning. And so you can potentially find more general codes there, and indeed you could sort of apply approximate error correction codes based on what we found, but it would work out quite well. So before concluding, I actually want to give all the credits of this work to my students. More work on the quantum fluctuator project, and David is the mastermind of all our theory work on quantum error correction, so all the credit to him. And now we are working together to actually implement this idea of the hardware efficient quantum error correction codes in our ND center system. So I'll leave you here with my conclusion and take any question that you might have.
Thank you, Paola. Questions?
Thank you for the talk. Hi, okay, thanks. I think you used this error correcting codes for spin defect, but is it possible to do it for like resonators or like CFD QED or circuit QED setups? So
as long as you have some sort of fluctuator which affects different qubits in a correlated way, then yes, definitely. And I think that like some of these like random fluctuators, they do appear because they're sort of correlated to materials impurities. And so I mean, of course we use it for our system, but I think it's more general than that. And of course, like this random fluctuator model is one particular that we study because we did want to do the experiments in our system. But there are other models for which we hope that you might be able to find like tailored error correction codes, which again will save you some hardware.
More questions? Maybe we can ask one quick question. So is it I guess in this situation where you have this common fluctuator, I guess unless all the G's are equal, there's no decoherence-free subspace?
Yeah.
Too bad.
So
it seems there's only one error and like so much Hilbert space.
Yeah. So, but in some sense, the code which like you end up creating, especially for small number of qubits, is relatively simple. So you don't need all that much of entanglement. So a lot of it is actually just separable state, which is quite different from a usual error correction codes. And I think that it's indeed related to the fact that it's quite close to a DFS in some sense.
More questions for Paola? Optimally positioned to be just equidistant from the two of us.
I have a question about the common fluctuator and when you have uncertainties in your couplings, the plot that you showed. Have you looked at optimizing the code for multiple G's within the uncertainty that you have at the same time? Like taking the mean of the cost function that you're optimizing for multiple values of G?
No, so here basically we optimize assuming that we know a particular set of coupling, and where we say, oh, well, we were wrong, and so how bad it would have been. But I mean, it could be interesting to potentially indeed do the optimization over a range of possible coupling, which I guess it's what you're.
Exactly.
Yeah, so. Yeah, I agree, but we didn't do it.
Thanks.
Yes.
More questions for Paola?
We should do it for the experiment where we probably do have uncertainty, and the number of qubits is going to be 2, so that's quite feasible, yeah.
More questions? If not, let's thank Paola again.